We're now going to take a look at another specific random variable, and this random variable is known as the hypergeometric random variable. And it unfortunately it has the word, or part of the word geometric in its name, and it's not typically related to the geometric distribution that we previously saw. In fact, this is more closely related to the binomial random variable than it is to the geometric random variable. But what we will do, as usual, is kind of state the experiment or any type of assumption, and then we will give some intuition behind the formulas for the PDF, and if there are any for the mean and variance, we'll also state those. All right. So let's define what a hypergeometric experiment is. So a hypergeometric experiment has the following properties, right, or characteristics. So one, we have a finite population or set consisting of, and we'll use big N elements. All right, so you can think of this as the entire population, right? But it's going to be finite, and that's key, right? Two, each individual, so each individual or element can be characterized as a success or failure, right? And so we've seen that, right? We've seen that in the three previous random variables, the binomial, negative binomial, and the geometric. They kind of have this dichotomous subset of the population where some of the elements or trials are successes, and they're either a success or a failure. So that dichotomy of two possibilities, right? And then the number of successes, right, in the population is denoted by A, right? So we have a big N that represents everything in our, you can think of this as your sample space. And then in your sample space, we have it where some of them are deemed success. So like those are the ones that you would want to observe when you make this trial, which we're going to describe here in a bit. And we're saying that there are A of those. So we're using A to represent the number of successes that are in your sample space or population. And then the third thing is a sample of size n individuals or elements, right, is selected without replacement, right? And that is the key. So that is what sets this experiment or this random variable apart from the previous three that we've looked at is the fact that now our sampling is without replacement, and what this means is that each trial is not independent of the others, right? So what this means is the trials are not independent, because each time we make a selection, right, then the sample space changes, right? And well, what are we interested in? Well, as usual, we're interested in the number of successes. So we're going to define, so let x represent the number of successes in the sample. Right? And here's the funny thing. We've actually answered questions that fit this model, this experiment, without calling it a random variable and calling it hypergeometric, right? All right, so, and you'll see when we kind of set up the PDF that, hey, I recognize that. Hopefully you do. Okay? So let's look at some notation. So again, we're going to use x to represent the number of successes in our sample, and we're going to use that symbol. Again, that just means that this random variable is distributed or follows, and now we're going to use h for hypergeometric. And this is how we will set it up. So the big N will go first. So that's your total sort of population, total number of elements in your sample space. And then the little n, that's the number that you're sampling out of this population. And then A is going to represent, again, the number of successes that are in that population, right? So now, the hypergeometric distribution or random variable, it has three parameters: your population size, your sample size, and then the number of ways that you can be successful on each try in that sample. Right? Okay, now the sample space, because these are three numbers and we don't really know how these numbers compare, it's a little hard to write down like what the sample space is. But we do realize that the sample space has to be finite, right? Because again, remember, the whole idea is we have a finite population and we're sampling from that finite population. So then, we will write down an expression in a little bit that's a little more complicated than what we've written down before. But what we can say is the sample space, right, must be finite, just based on how everything was described, right? We're starting with a finite population, so any subset of something finite must also be finite. So the sample space must be finite, right? Okay, so let's focus first on the PDF. So let's, we haven't drawn a picture in a while. Let's draw a picture. So, we have a total N, right? So we have a total population of size N, and it's broken into, again, this dichotomy of successes and failures. And we know that there are A successes here. So let me say that this portion of it represents the successes. And then that leaves the total minus the A. That would be your failures, right? So this would be the number of successes, and then over here we have the number of failures. and we're choosing n out of this, right? And we're basically trying to count, how many of those n's will be failures and how many of them will be successes. Well, we're really interested in the number of successes, but really, because there are only two possibilities, once you know the number of successes, again, if you take the difference between what you've sampled and how many successes you have, then that will leave how many failures you have, right? So again, it's this dichotomy that it's one or the other. Well, let's see. So first we might ask ourselves, as far as the sample is concerned, how many ways can I choose n things out of big N things? So basically, let's write down a formula for the number of elements in the sample space. We know it has to be finite, so that's good. Well, that's simply your little n. Well, actually, let me write it this way. Out of your big N, you're choosing little n things, right? That's it. That's the number of elements, or I should say, the number of ways that you can choose your sample out of your population, right? The reason why I'm using this notation is because I'm going to use that classical approach of probability theory to say, okay, well, what is the probability that x is a particular number, right? Now, so we want to then try to figure out the number of successes. So how many ways can I get a success choosing little n out of big N if there are a successes in my population, right? Well, the probability that my random variable will be equal to a specific number, then it means I'd have to figure out the number of successes, or the number of ways that I could get x successes out of this divided by this, right? So I know in my denominator I'm going to have my big N choose little n. Now I have to figure out what goes in the numerator. Well, if I want to observe exactly x number of successes, then I'd have to make sure that out of the a here, I have to choose x of them. So I'd have to choose, at the top I'd have to have a and then choose x out of that subset, and then I'd have to make sure that the remainder, right, so the remaining ones are failures, right? If I want to have exactly x successes, right, and I am choosing little n total, then I would have to first have the x number chosen out of my number of successes, and then the remainder would be chosen out of the n minus a part of my population. So this, and then choose little n minus x, right? So these two numbers must add up to, again, everything that I have here, right? We're choosing x out of this subset, and then we're choosing the remaining n minus x out of this subset, and then divided by the total number of ways of choosing little n things out of n things. And this is exactly what we've done in the past using our combination formula, but we've never really stated that it was a hypergeometric experiment, but in fact it is, right? So that is the formula. Now here comes the kind of tricky part in terms of writing down what exactly defines the sample space, right? In other words, what are the actual possible values of x? Well, it's hard to say because I don't know how these numbers compare. I don't know in terms of the number of successes. Do I have more successes than the actual number that I'm going to be sampling? Or do I have less number of successes than the number that will be sampled, right? So it takes a little while to argue and come up with this formula, but I've come up with a fairly decent formula that can be applied to figure out what are the possible values of x, right? Now that we know how to compute the probability, right, it seems like it's a little bit backwards. We've figured out how to compute the probability, and now we're trying to say, well, x can take on these possible values, right? But now let me write it down. So for x, so one thing we know for sure, because it's a count, it has to be an integer. So for x, an integer, and satisfying this little inequality. Right, so satisfying, and here's the inequality. Let me write it below. So what you can take is find the maximum of this number, or these two numbers, either 0, right, or your little n minus big N plus your a, right? So if you take the number that you're sampling minus your population plus the number of successes, right? Whatever that number is, compare it with 0 and see which is bigger, right? So for instance, if this ends up being a negative number, right? If this ends up being a negative number, then your max will return 0. If this is something positive, then it will return this number, right? So figure that out, and then less than or equal to x, which is less than or equal to, and then the upper bound has to be, this one's a little bit easier, but it's the minimum of your little n and your a, right? And here is the reason why. Is if you think about it, the number of successes that you are going to observe, it can't be any bigger than how many the size of your sample, and also it can't be any bigger than the number of successes that are in your population, right? So these two numbers are natural, like upper limits or upper bounds on the number of successes you can observe, right? So not a lot of resources actually state this inequality, but it is useful because it then gives you an idea of, okay, what are the possible values of x? But because we don't know these three numbers, we can't always say that, okay, it starts from 0, or it might start from something positive. That's the whole point here, right? And then these two now represent possible upper bounds. It just depends which one is smaller. All right. So that's the PDF, and then this is these are two formulas that you can use to figure out the possible values of x. And it will, once we look at a specific example, it will be clear how to use these, right? But keep in mind that it has to be an integer. It has to be an integer because this is still a discrete random variable, so we have to have gaps between it. This is not referring to an interval. It's just saying that, okay, it's integer values that are between these two numbers, right? Okay, so that's the PDF, and the other piece that we need is to state the mean and the variance. And the mean, right, or our expected value of x, how many successes do we expect? Well, the mean is actually fairly easy. It's n times, so this is the number of trials, right? And if you think about it, in the proportion of successes is A out of big N. And that's the formula, right? So this looks a lot like your P, like your N times P from the binomial random variable. It's just that now your probability of success, if you will, it depends on how many successes do you have in your total population, right? So that part is very similar to the binomial. The variance, well, not unfortunately, but it's just the way this scenario works out. Your variance is not so similar. Right? So the variance of your hypergeometric random variable, you have your n, and then you have times a over big N, and then you have 1 minus a over big N. So that, again, looks like your n times p times 1 minus p, but then there's this other factor because of your sampling without replacement now, and then you have your big N minus n over big N minus 1, right? So the formula for the variance of a hypergeometric random variable is a little bit more complicated, and this factor here is called a finite population correction factor, and it's just a fancy phrase for, because we're sampling without replacement now, independence goes away, and then there are some other things that affect the variance, and it's all accounted for in this particular formula. It's not a nice thing to have to derive, and I wouldn't have derived it anyway. I want to focus on the type of experiment, what the PDF looks like, any formulas for mean and variance, and then do a couple examples. All right. So let's see if we can do an example here. And all right, so let's scroll down here. And what I'll do is not necessarily do like a story problem. Let's just again state that it's a hypergeometric, give you some values, and then we'll compute some probabilities, and then maybe the expected value and the variance and possibly standard deviation, right? So let's say we have a population that consists of 25 objects or elements or people, and we are going to sample, let's say 10, and 5 of them represent success, right? So say 5, right? Let's see if we can just go ahead and write down the PDF and then actually make sense of this inequality right here, right? In fact, if you want, we can go ahead and work with the inequality first, right? So we have a big population of 25, and we're sampling 10, and our number of successes is here. So if we compute our n minus a, little n minus n, big N plus a, that's equal to 5 minus 25 plus 5. So if you look at this ends up being negative 15, right? So when we take the maximum of 0 and negative 15, obviously we're going to get 0, right? So in this case, it is possible to get no successes at all, right? Because since there are only 5 ways to be successful in this population, and we're choosing 10, there are enough failures left over so that we could end up choosing all 10 failures. So that's why this is saying that it is possible to observe 0 successes. If the population didn't have that many failures, then maybe when we sample the 10, we're guaranteed to get at least one success. In that case, then the maximum here would be 1, right? And so forth. So that's why this little calculation is helpful. It tells you essentially what is the smallest number of successes you can hope to observe in this particular sample, right? And then as far as the upper limit now, so then we just have to take the minimum of our 10 and our 5, and the minimum there is 5, right? So putting these two things together, this tells me that x can be any positive integer or any integer from 0 to 5. So 0, 1, 2, 3, 4, 5, right? So that's our sample space. Now let's write down the PDF, right? So that's going to be, so for the success part, we want to choose out of the 5, obviously. So we're going to have the 5 choose X. And then that means the remaining 20, that represents my failures, or the ones that I don't want. So then 20 choose the difference between the 10 and so then right here, your 10 minus x, right? And then this is all over your 25, choose 10, right? So in the denominator, it's these two numbers, right? The successes and the failures, put it together. That's going to give me my big N. And out of that, we're choosing this number of successes and this number of failures for a total of the little n. There we go. So that's our PDF. And again, much like the negative binomial and the geometric, we don't have even like nice tables for the CDF of something like this, right? So any cumulative probability that we have to compute, it means we're going to have to do it by hand. All right. So let's do part A. So part A, suppose we want to figure out the probability that we will observe exactly 2 successes, right? So 2 successes, right? Out of a sample of 10, that means we would have 8 failures, right? So it's just a matter of evaluating now. So we're going to have our 5, and we're choosing 2 out of the 5, and then out of the remaining 20, we're going to be choosing the 8. And then that's divided by the 25, choose 10. And so let's see, this is our 5 factorial over 3 factorial, 2 factorial, and then times 20 factorial over 12 factorial, 8 factorial, and then divided by our 25 factorial over, and then 15 factorial, 10 factorial, and that all simplifies to, so 3 decimal places, 0.385, right? So roughly, a 38.5% chance that we're going to observe exactly 2 successes in this sample, right? Now, suppose we wanted the probability that x is less than or equal to 2, right? Now, if we look at it, this is where this information is helpful, and you can decide, is it easier for me to accumulate the probabilities that's stated here in the inequality, or is it easier for me to consider the complement? Well, because there are 6 possible values of x, and right here we're interested in this half of the 6, it's not much, it's not any more work to use the more or less work to use the complement, right? So we're basically looking at these possibilities now. We are going to have to add up the probabilities that x is equal to 0, or x is equal to 1, or x is equal to 2, right? If we did the complement, it would be 1 minus the probability that x is equal to 3 or 4 or 5. So it will be pretty much the exact same amount of work, right? Now let's see. So 0 successes, that means everything would be chosen from the failures. So again, let me write it out. It would be 5 choose 0 times 20 choose 10, all 10 out of the failures, divided by. Now, since the denominator is going to be the same, what we can do is just keep we can write these 3 probabilities as one separate, as one fraction, all with the same denominator, 25 choose 10, right? Which is what we have right here, right? So you can look at things like that to kind of minimize the amount of arithmetic operations you have to do. For this one, it's 5 choose 1 times 20 choose 9. And then this is the one we have right here. At least this numerator now is now the third term in this numerator. So the 5 choose 2 times the 20 choose 8, right? And this is what we, unfortunately have to, not really unfortunately, it's just the way it works. It's too difficult to come up, because you're talking about 3 parameters, a big N, a little n, and an a. It would be very tedious to compile like a table of values that will be helpful in situations like this, right? And then, so 5 choose 0, that's 1. 20 choose 10, that's 20 factorial over 10 factorial and 10 factorial. And then 5 choose 1, that's 5. I know that's 5. And then the 20 choose 9, so 20 factorial over 9 factorial, 11 factorial. And then this is the one that we just did. 5 choose 2. I think that comes out to be 10. I'll write it as 10. And then this one, I'm not sure what that number is. Some big number, I'm sure. 8 factorial, 12 factorial, and then all of that is over the 25 factorial over 15 factorial, 10 factorial. And let me write the separate ones together. So the probability that x is equal to 0 to 3 decimal places is 0.057. The probability that x is equal to 1, that's 0.257. And we computed this one earlier, the probability that x is equal to 2, that's 0.385. And then adding those all up, we get almost 70%, 6.699. That's the probability that we will observe at most 2 successes in our sample, right? And if we do, let's finish this up by doing the usual mean and variance calculation. So the mean in this case, or the expected value, so like how many successes would we expect if we did this particular sampling? Well, the formula is our, let's see, so that's, yeah, so it's our big N times A over, or actually, let me write it this way. It's or sample the sample size times the number of successes over our A. So that's our 10 times 5 over 25, and that's 2. So that's how many we would expect to get in a sample like this, a sample with replacement. And then the variance, again, a little bit more complicated. So it's going to be the... Now, what you can do with this is, so let me write it out. So you got your n, a over big N, and then times 1 minus a over big N, and then you have your n minus 1, or n minus n over n minus 1, right? So in this case, we got our 10 times 5 over 25 times 1 minus 5 over 25 times our big N is a 25, and we're sampling 10, and then we have 25 minus 1. Right? So let's see, what does that come out to be? So this we know is 2, right? So we could have actually brought that in. That's 2. And then here we have, this is 20 over 25, which is 4/5. So we have that. And then here we have 15 over 24. And what do we have there? So we got 8. Well, actually, let's do this. So we got 6. Oh, look at that. Our variance is 1. We got 30 over 30, so we got 1, which then means our standard deviation is also 1. All right. So that's our hypergeometric. Again, what's nice is that we have specific formulas. We just have to work on making sure that we know which of these experiments is actually in play, ensuring that we'll actually use the right formulas, right? So it's focusing on the differences, the different aspects of the different experiments, and what really sets the hypergeometric apart from the previous 3 is that now your trials are not independent, because the sampling is being done without replacement, and therefore the sample space changes every time you pull. Whether you pull a success or a failure, it changes your sample space. All right, I'll see you in the next video.